So I think we just started soils on um, Wednesday. I talked about how I taught soils and didn't think I was going to like soils and wound up loving soils and all that. And so, anyway, parent material. Um, this was the part of the soils class that when I got to, I mean, the book began with this, and this is where I was like, oh, I'm gonna like this actually, because it was geology, and um, I guess in a sense I didn't quite realize myself how fascinated I was with geology, um, but uh, I've always been kind of fascinated with rocks, and I've got my youngest has got that same fascination. Um, anyway, uh, there's one of the things I talk about in my biology class, and I'll reiterate for those who didn't didn't take that class. Uh, what we have is we have these these plates, tectonic plates is sometimes what they're called, that move around on this planet. Throughout the history of the planet, they've been submerged, and they one rides up underneath the down under each other, and the other one's on top of each other. And my daughter's making hand signals at me. So anyway, there's this constant change, ebb and flow, and over millions of years, we've got continents that have been totally submerged underneath the existing continents now, and ones that are exposed now were submerged under the ocean at points in the past. And we have some places on this planet that appear to maybe been exposed from the beginning and never been under or over, and so or are now over, and always have been. But it's kind of fascinating to study and how the Earth actually does renew itself. Um, Soils that are exposed and have plants growing on them get depleted of minerals over time. And even though decay happens to put those minerals back into the soil and kind of replenish that, some things are just lost. They're not, we can't restore everything because animals eat it and carry it somewhere else. And um, that part of the plant isn't there to decay in the end. So slowly over time, soils are depleted. Um, and there are several ways in which the Earth can restore that. One of those is volcanic activity. Okay,
I have
so
a question. Sorry.
sure.
Are we supposed to be seeing the slideshow yet, or?
Yeah, you are. Did I not? I didn't. Did I? Thank you for saying something.
You're welcome. I didn't want to.
No,
Nope.
I want you to see that, so I appreciate it.
Okay.
Okay. Okay, I think this is the slide I ended off on. I hadn't gone anywhere with it yet, and I really hadn't started talking about anything on here. I'm getting ready to. I'm leading right up to this right here. Wait, there's my cursor right there. Okay, so volcanoes will, throw out this ash and lava rock, volcanic rock, and that lava rock has a different consistency depending on what was underneath that volcano. Okay, those volcanic events that go deep down into the earth, they are melting rock down there, and that that rock's going to be different just depending on what that particular part of the earth is composed of. And as these things move around, and like I said, you get subduction and all of that of tectonic plates under each other, um, and then it can change. Okay, but those rocks get melted, and that all gets thrown up, and some of it's total, is ash. And ash is incredibly volcanic ash is incredibly mineral rich, and so that really can help the fertility of land around. And then the lava rock, when it solidifies, it's full of minerals and things too. And over time, that is one thing that soil is going to be made out of. Okay, is that volcanic rock. Um, and the name for that is igneous. Okay, igneous rock. We also have sedimentary rock. That gets deposited, the sediment gets deposited by glaciers, water, and wind, and these are layered rocks. You can see when you look at that type of rock, you can tell that there's these kind of like layers on it. So you know that that was formed by sedimentation, and that's where you're going to find fossils of past living things. Typically, is in sedimentary type rock, um, and these types of rock are just what's exposed. Erosion can expose those to the surface. Again, if you get plates colliding, the type of rocks that sometimes get thrown up, uh, were things that were formed by sedimentation in the past. A lot of times, though, when you're looking at whole tectonic plates and where the ridges collide, and you get one, like a mountain range thrown up, uh, that's all exposed rock that was at one time down in the earth. It's underneath that plate, and you're getting that plate thrown up there. So you like look at our Rocky Mountains; those are like some of the newest mountains from a plate buckling. I think it's not so much collision, but it's buckling. The plate buckled under pressure, and so that underneath stuff got pushed up. Um, Here in Oklahoma, we've got like 5 mountain ranges. Can you believe that? 5 mountain ranges. They're really old. Um, the youngest, I think, it's the youngest of our ranges, and the tallest are the Arbuckles. Okay. Um, but a lot of those rocks are what's called metamorphic. They start off as igneous or sedimentary rocks, and then under pressure and heat, okay, either experienced when they were underneath or at the time of a collision or a buckling of the plate they're on. Those processes are pretty catastrophic. Okay. There's a lot of pressure and friction heat that can happen in those processes, and that can change the rocks as well. So you get these types of rocks, and bare rock will be broken down by processes into soil. That is where soil comes from. And that's how new soil is made. Okay. And so, depending on what kind of rock was there for that soil to be formed from, is going to determine a lot about the composition of that soil, how nutrient rich that soil was, at least to start with, and may still be depending on how long it's been there. And then, of course, climate plays a role too, because climate varies throughout the globe over the planet. And so, that climate is going to affect weathering. And of course, weathering will uh, and the type of weathering will determine kind of how fast that rock breaks down um, due to those pressures. You got I talk, and I will talk obviously in this class more about how plants play a role in breaking rock down to form soil. But if we just look at the physical aspects of it right now, we look at climate. You're looking at wind erosion. You're looking at water erosion. You're looking at freezing and thawing. That requires water, obviously, but temperatures issues on that. Water gets into crevices, and when it freezes, it expands, and that can widen a crack or crevice in a rock, causing the rock eventually to break into two instead of one. Um, and also, it just simple water dissolving the minerals on the surface as it flows over is going to erode away. Okay. But that carries the nutrients away. That doesn't necessarily mean they go all the way downstream and wind up in the ocean. That carries them a little bit away. They may settle out, and they'll add to sediment. If you have spring floods, okay, and low lying areas are flooded with areas draining off rocks, but that sediment gets kind of deposited out before it gets into the actual channel of the real stream, and the waters recede and they deposit that stuff as they recede. Then you wind up with new fertility being added to these lowland areas, and that's why some of your best farmland is usually right along creeks and rivers that often flood, and you're kind of like, wow, why do people keep planting crops there when they just know it's going to get flooded out? Because it doesn't flood every year sometimes. And when it does grow a crop, it's usually often makes up for the losses of the years that have flooded, because it's a really fertile, rich soil, and will really grow and produce a bumper crop, so to speak. Um, so our deserts don't see a lot of rain, so you're not going to have water erosion happening there. You have some wind erosion, but unfortunately, what happens if you've got areas that are high in wind erosion over time, all the organic material and the good stuff is kind of lighter and gets carried away. And then what you have left is your bits of rock, okay, your sand. Um, and so we say these are poorly developed soils. Uh, and some evidence shows that some of our desert regions on this planet weren't always like the Sahara. Um, it's been hypothesized for a number of years that the Sahara was at one time this lush green valley. Now it's one of the largest deserts in the world, but it was possibly a highly civilized area, even a highly colonized, huge population area, put it that way, for the time period on the planet. Um, what happened? Well, looks like we may have had some climate change. Okay. Um, they the plates are tectonic plates are always moving, and they think actually that the African plate shifted slowly over time, and that resulted in climate change for that area, and rainfall changed. Um, it's possible that if enough people were living there, that they overtaxed the area. Now, uh, it, that's still under study. Obviously, there's not a lot. I mean, not everybody's on that bandwagon that that was a lush valley, but there's more evidence growing to support that idea. The question now becomes: were the people who lived there at the time actually agricultural yet? Okay, or were they still just kind of just gathering and hunting and hunting gatherers type society? And that's not. I haven't read any evidence yet on determining that factor. But one of the things that has been said was, well, if that is the earliest, that would probably be the earliest agricultural farming um, civilization that we would know about. Okay, because that would predate what we know currently of anybody of people settling down and doing agricultural um, uh, societies. Uh, they could have overfarmed the area. Okay, overfarming is bad for the soil, and it will deplete the soil, and it can turn a fertile area into a desert. Okay, pretty much happened here in the Dust Bowl. Okay, we had two things: we had drought, and we had overfarming, poor farming practices. We had clear cutting of our trees that are really good for holding soil, and then we had drought, and we had high winds, and yeah. Um, if the rain hadn't come back, and if conservation efforts hadn't been employed wide scale to try to recover the soil, we would probably be looking at a different surroundings than we have here. Now, this part of the state was not as affected as bad. This part of the state got more rain. This part of the state, people were able to farm and grow crops here somewhat even in the Dust Bowl, though. It was a hard time period. My grandparents lived here at that time period. My grandma talked about trying to survive through the 1930s. But people in this part of the state were much better off than people out west. Okay, it was really rough out there. Um, so a lot of topsoil blew away, and when the topsoil blows away, what you got left is the soil underneath that doesn't have a lot of nutrients in it. Where you have areas of moderate rainfall, which is kind of where we're at, you typically have well-developed soils. You don't have too much rainfall, so you don't have a lot of water erosion. You have a little, but not a lot. The nutrients typically are able to decay from the organic matter and stay right there in the soil to be used again for other plants growing. So that's your ideal situation. And then areas of high rainfall, we have the problems with excessive water flow going through the soil, and we get two problems. We get possible topsoil being washed away, but something we also don't think about a lot is that the water that doesn't just run off immediately sits in it. It'll percolate down through the soil, percolate down through the soil. And so even if you don't have like flash floods that just run off and take the topsoil with it, you just have these constant steady rains all the time. That's going down through the soil. It's like, oh, it's a good soaking rain. Well, that's good every now and then, but if you've got that constantly, that's still going to leach important minerals. The water will dissolve the mineral into itself, water solvent, universal solvent, and it'll carry that down through the soil. And where that'll wind up is getting deposited usually further down into the ground where it's not accessible for plant use. And in a sense, we do want some of that type of rainfall to happen because that's what replenishes the aquifers that are underneath the ground. And that was a discussion in last class. We were talking about shortage of fresh water, potential future shortage of fresh water on the planet, and we were talking about how we are depleting the aquifers under the ground because we drill wells down into them, we use them, and we irrigate out of them. The western Kansas, Oklahoma Panhandle aquifer out there, called the Ogallala aquifer. Ogallala. I can't. I said it a while ago, and I've got my tongue all twisted. Ogallala aquifer. There you go. And it's running dry, And back when I was in college taking these soil classes, they were talking about how it was going to go dry and it's going to go dry soon if they didn't do something about it. And one of my students who said when she was living out there, they said it's going to go dry in 15 years. And that was like, I think she said like 10 years ago. So it's critical. It's a big concern amongst agriculturalists in particular, because if when it goes dry, we can't farm out there anymore. Um, and also the people, the towns that live with wells going down into it, where they're gonna have to bring their water in from somewhere else. In fact, they already are, I think, in some cases. Um, and it just doesn't rain enough out there to replenish it, because that's not an area of necessarily moderate rainfall. It's kind of on the, it's not a desert yet, but low side of that. Um, One of the problems is we're raising crops out there that really shouldn't be raised out there. It requires too much water for the area. Um, we do still want to be able to use that area to grow food, though, because we need to grow food. But the question there, and one of the things that scientists have been working on, is trying to develop more drought-resistant plants, more drought-resistant crops. Things that can we get a wheat variety to grow out there and require less water than what we're currently doing? Um, and they have done some progress on that, being able to get um, a little less water, but not enough, really. Okay. So those are some of the challenges that we face in trying to deal with different soil types, and also preserve the soil types that we have. Not deplete them, but keep them useful to us, because we tend to deplete them a lot faster than nature's going to renew them. Okay. Um, there is a big volcano out there, by the way. It's underground. It encompasses, I think, 3 states. It's the western part of the Oklahoma Panhandle, that corner of New Mexico, and Kansas, southwestern Kansas, maybe 4 states. Anyway, it's out there in that Black Mesa area. But there's a buried. I think you can see it if you're flying over from a plane in the air. But there's a caldera there, as they call it. It's a collapsed volcano cone, to where it's not like a super volcano the size of Yellowstone or anything like that, but it's a pretty good sized one, and it's considered dormant. It's not considered extinct. It's not considered an extinct volcano. It's considered dormant, which means that at some point in the future it can become active again. It's active underground. Okay, it's still producing heat and steam underground. I don't think it's got any major vents to the surface like you see at Yellowstone, where you've got all those hot springs vents, but it's there. So that area could get replenished at some point in the future, but who knows when. So climate, yeah, okay, digressed a little there. Um, and then, of course, our living organisms. In soil, there are many kinds of organisms, roots, and other plant parts that are going to function to either, to enhance or at least gives different characteristics to the soil. So we have bacteria and fungi that decompose organic material from dead leaves, plants, and animals. Uh, we have roots and other living organisms that are going to produce carbon dioxide, and then that combines with soil. And those of you from biology last year might remember I talked about this a bit, that carbon dioxide dissolved in water forms an acid. It's a carbonic acid. Okay. Uh, that is why when we get a lot of carbon dioxide in the air, we are more likely to have acid rain, because that carbon dioxide will dissolve in the water, in the rainwater, okay, as it falls down. Um, Also, that is why Coca-Cola, or any of your pops, but everybody always likes to pick on Coke, okay, is so acidic. All right. That's carbon dioxide dissolved in water. We've pumped it into the water under pressure. And as long as that bottle or can is sealed under pressure, that carbon dioxide is going to stay in solution. That's something we don't talk about in this class much, but it's my chemistry class. I've talked about that. Under pressure, that carbon dioxide will stay dissolved in the water. When you release it, that's why it fizzes or spews, is because all that carbon dioxide now comes out of solution in the water. But a small amount will stay in solution. Of course, it takes a little bit of time for the first release is a first equalization, but you still have bubbles. You'll have fizz for some time. Unless you let it sit overnight, it's not going to go flat. It'll still be fizzy, and that fizzy is the carbon dioxide that is dissolved in that water. And if you're to take a litmus paper to test for acid and stick it down into that pop while it's still got the fizz, it'll turn out acid. I mean, that's why. Okay. Carbon dioxide dissolved in water makes acid. Okay. And that's actually a good thing down in the soil because that again can break down rock bits um, and release minerals out into the soil for plant use. Okay. Um, down above the soil, we don't want that coming down as rain because that can destroy the leaves of the plants, it can destroy the stems of the plants, it can do bad things for the plants. But when it's down in the soil and a byproduct of what's being released and going on down kind of below the roots, below the plant, then that can serve as a good renewing cycle process. Okay. Um, Also, we have small animals that alter soil by their activities, such as digging tunnels and living down in the soil, and then waste products also collect there. And then you have soil, animals just defecate on the surface of the soil too, but you have some that dig their little holes and they'll cover it back up, and that's fertilizer. Okay, those waste products carry the products that we don't use, so that again returns some of that material that was once taken away as a plant when an animal ate it back into the soil. Um, and then what we call humus, and humus is well, it's humus. Humus is food. Yeah, garbanzo beans, chickpeas, what do you want to call it? This is humus, one M instead of two. Humus. Um, this is partially decomposed organic matter, and it gives soil its dark color. And that's why oftentimes when you're looking at soil, you have a dark soil or you have a lighter colored soil, and we say, oh, that dark soil, that's the richest and that's the best soil. And usually that's true. Um, you find some of the lighter colored soils, if you go out west in western Oklahoma, uh, you run into the kind of the red soil. And that doesn't necessarily mean that it's not good soil. You can grow some pretty good stuff out there, but uh, that is because there's a lot of iron um, in that soil. It gives it that red color, and it's mostly what you find out there is what's called an aluminum silicate clay. All right. It's kind of sticky. It's high in iron. It's high in aluminum, and it's got some issues. Okay. There's the people. When I, obviously going to school at Stillwater, we studied that local soil a lot, and there's some things that you have to definitely keep an eye on and do with soil out there in order to grow good crops on it. It's a little easier here. We have darker soil here. Okay. But we still have issues here too. Okay. Um, Topography. Looking at my time. Okay. Topography, what we mean by that is, so we're looking at surface features. If you see a topographical map, that's one that usually talks about your elevation and give you all sorts of information about what's on the surface, the features of the land. Um, and so, speaking of elevation, if you have a quick increase in elevation, that's a very steep slope that you're looking at on that map. And so if we see steep areas, steep slopes, um, that's an area that soil can potentially erode away very quickly. It's exposed to wind. Okay, steep slope is going to be hit more by wind, and also water is going to run off of it very fast. And yeah, ice is kind of like water in many ways. Um, so those, if you're looking at steep rock, that ice could play more of a physical factor, I think, than it would necessarily just on a hill, um, because again, being able to get to crevices, okay, and expand. But your steep areas are often more exposed. Okay. Conversely, if you've got flat areas, they can be poorly drained, and therefore you may get collection of water in those places. And then you have pools and ponds appearing, which is not bad for the environment. Things live in those areas, and we need some of that. But if you're looking at development of the soil in that area, that's going to stagnate. That soil isn't going to continue to develop probably much if it's underwater. Okay. So your ideal topography is like a gentle slope, kind of low rolling hills are nice. Okay, you get some nice drainage, but it's not fast water drain off that would cause erosion. So I live on a hill, and this is an old farm. It was farmed back in the 1800s, and my grandparents bought it in 36, and sorry, this house was built in 36. They bought it in 46, but they knew the people they bought it from, and they had lived down the road back in the 20s even. Okay, so they knew the area. I think my dad and grandpa had actually farmed some of this land before they bought it, and rented it from the people who owned it. So the house had been there was a house here before this one that had been built like in the 1800s, and then it got torn down, and this one got built in 36. Um, but this house is built on a hill, and it is I swear, the worst soil on this entire section mile. So you know why they built the house here? Okay. This is, everything else could be farmed. And this is a rock. It's a rocky hill. It's got a little shale on it. You can't dig down anywhere without hitting rocks. And I know biology people have heard this story already. So anyway, uh, but one of the things that happens is I fight erosion on this hill. Okay, down my driveway, water my driveway becomes a river when it rains a lot, and so it's constantly I'm putting gravel on my driveway. I live a half mile off the road, so I have a half-mile driveway I have to maintain, and we put gravel on that road, and here comes the rain, and all the gravel winds up in the creek. Right down my driveway, just washes. And then I've got these divots and stuff on the side. Well, my grandparents fought that same problem, and one of the things they did that I'm probably needing to go in and redo is they built what's called a swale. Okay, SWALE. And what that is it's they kind of dug out a grassy, they dug out a little channel by the side of the road, and it's a very gentle okay channel, and then they put grass in it. Okay, I think they probably mostly Bermuda grass, I'm guessing, because that was the big root holder of the time period when they did this. And what that's supposed to be is that's supposed to be a channel to carry the water away from the road to the creek at a slow pace. Okay, because all that grass is supposed to be growing in there to slow down the water and its movement, so it doesn't just rush down the road as fast. I mean, it's a raging river going down the road if we get a downpour. So that is not working right now. Partly because I think it needs to be kind of cleaned out and rebuilt, and that takes time and money and equipment that we don't currently have at the moment. And yeah, and the other side of that, so here's the road, here's the little swale, and there's a terrace that they put up here, and then on beyond that is a big field, okay, that sits out right in front of our house. And again, water draining off of that field would be stopped by that terrace, so it wouldn't go into that swale and create too much water coming off of that. But again, you're trying to stop the erosion off the field. So it functioned in quite a few ways, and that's just a soil conservation technique that is used to try to help slow erosion. So it's part of that. I'm saying kind of gently rolling hills is ideal. You want a little drainage, but you don't want too fast. Okay. So we talk about soil texture. I keep talking about all these minerals. We need these minerals. Okay. One of the things that agriculturalists do, botanists do, anybody, I mean, I've done it once, I think here, need to do it again. My dad used to do a lot for the farmland, is we take soil samples and send them off to have them tested. And when I was at OSU, I of course taught the soil science class, so I taught how to do this to my students. I taught the labs, and so this is what we did. We did the lab stuff. But my graduate student office, we was 5 of us in an office together, and we were right across the hallway from the main doors going into the soil laboratory. And on their breaks, the soil lab techs would come in and talk to us, or we'd go, and we didn't really go in the lab much because we weren't supposed to be in the lab, but we would stand on the hall talking and stuff. And anyway, so very, I guess, involved, so to speak, in the soil testing that was going on down there. And so what you do is you take the area you want to be tested. It could be your garden, it could be your yard. You go and you take a shovel and you dig out a little bit, and you take that and you put it in a bucket, and then you go to like another corner of the area and you dig that out and put it in a bucket, and you dig out just a little scoop every place, and then like once in the center, uh, and you mix all that together. Okay, and then you take out a certain size of that sample, and what that does is that hopefully will kind of average the best and the worst parts of your plot of land that you're trying to get a sample from. And you send that off down there to them, and they will, and you can send it through your extension agent. And anybody can use the extension agent. You do not have to be a farmer to take stuff to the extension agent. They work with anybody in their county for anything you need. So if you've got a yard in town and you want to know how much fertilizer to put on that yard, okay, to help the grass and what kind of fertilizer, you need to do this because this is one of our sources of pollution in cities that we could do something about, but we don't. Everybody wants these beautiful yards. And it's like, well, I know if I go and buy a bag of fertilizer and throw it out there, it'll make the yard green and pretty. And so they do that. And in most cases, they're over fertilizing and they're often putting nutrients on there they don't need to put on there because they're not missing that. They're missing something else, really. Or they're only missing one of those things and not all of it. So I don't know what the cost is now. It used to be $6. Okay, it used to be $6 to go have one of these soil tests done, and you get this printout of everything that you have, and then kind of what ideal soil would be, and gives you an idea. They make recommendations on what kind of fertilizer you need, how much of the different nutrients you need or don't need, and that is the smarter way to fertilize. For farmers, they have to do that because it is too expensive to go buy these fertilizers of, if you don't need nitrogen and you're paying money for nitrogen, you're throwing money away. And phosphorus, potassium, those are the big three, okay, fertilizers. So they do that. And also they tell you what composition your soil is. Okay, so they give you the mineral contents and they give you the basically nutrient mineral contents, and they tell you what proportions you've got here. And that's what we're talking about is there's three main components in soil. There's sand, there's silt, and there's clay. Okay, and the definition of that is sand is many small particles bound together chemically, and usually it's gritty. It's that sand. It's that silicate uh, chemical structure, uh, and it's the largest. Um, it's the largest particle in the soil. Then we have silt, and these are particles that are too small to be seen without a microscope, but you can see them under the microscope. And then we have clay, and clay can only be seen with an electron microscope. These are very small atomic, features, uh, or small atoms clumped together. Those are called micelles. Micelles, that's a term it's used multiple times because I use it when we're talking about the phospholipid circling the wagons too. But these are kind of like, I think little atoms in kind of little circular structure. Clays are negatively charged. So they're going to attract, exchange, or retain positively charged ions such as magnesium and potassium. And, where I use that analogy of, sodium and chlorine are held together, but if something more positively charged, more attractive, then sodium comes along, chlorine's gone. Yeah. You've got the opposite of that kind of going on. We've got these negatively charged clay particles. They're going to attract your cations. Magnesium and potassium will abandon chlorine to stick to this clay, okay, because it's very negatively charged, a stronger negative charge than what's holding the compound together, the ionic compound together. So things will come along and dislodge one another. Okay, so magnesium will be released under certain circumstances, and something else will be bound to the clay instead. And this is a constant process that goes on. So you want a little bit of clay, but you don't want too much clay, because too much clay is going to bind up too many of these things that are needed. Okay. So your best agricultural soils are composed of 40% silt, 40% sand, and 20% clay. Okay. That's ideally what you want. And so if you do a soil test, they'll send back the results telling you what percentage of sand, silt, and clay you have, and kind of how far off you are from what you want. It is not uncommon for soil amendments to be recommended. And one of the things is that if you've got too much clay in a soil, which is pretty common, you can actually bring sand in. Okay, if you're looking at a garden spot, not an entire agricultural field, but you're just like looking at your yard, you're looking at a garden spot, you can bring sand in and then till that into your soil, okay, to try to get it into more of this type of percentage distribution, okay, to reduce the clay and bring up the sand. And for silt to change that, That's kind of more of an overtime thing, but one of the things that can help is to use organic matter. Okay. Was the organic matter decomposes, it kind of helps add that over time, that can get into that silt category, or at least it mimics it. Okay, so if you have too much sand, though, that's called a coarse soil, and the water is going to drain too quickly. And so it doesn't matter how much rain you get, the plants will only be able to access that water for a brief moment because it's not going to be held in the soil. It'll go away. So if you've got too much sand in your soil, that's where, again, organic matter. For biology students last semester, I talked a lot about peat moss. Okay, peat was something that it's a soil amendment you can add into the soil, because peat will, it's dried moss, dried dead moss remains, but that those cellulose in there, the cells will hold that water, and like a sponge, and they hold on to it a lot longer than it would be there in that type of soil, because that's just going to drain away. Okay. Clay soils allow a little water to pass, but because of their charge, they'll hold on to that water and still not let the plants have it sometimes. But you can have two problems. You can have too much water and the plant roots get waterlogged. They can't exchange water. Or you have just water being held too tight, the water that's there being held too tight, and the plant root can't access it. Again, that peat moss also. I used to use a lot of peat moss here, trying to amend my clay. I have soil that's high clay on this hill, clay and rock, and so I'm always trying to improve that organic matter quality of my soil. Um, and of course, down closer to the creek, we've got occasional floods. Comes out. We deposit all sorts of new material down there, so that's a nice dark soil down there. But up on the hill here, it's still kind of dark in color, but it's not a good mix. Okay. So productive agricultural soils are granular, with pore spaces occupying between 40 to 60% of total soil volume. And here, its particle size is more important than total volume. One of the tests, though, that we did, and we'll see, I've said I might see if we can do some of these soil tests, because I think we've got the equipment in the lab, because I think Dr. Allman had her students do them, because I think she actually taught some soil science classes for us there, NEO. The is just use a graduated cylinder, 100 milliliter graduated cylinder. You put the soil in there, and after you got to do some stuff to it first. You put it in there, and you let it settle out, and then you measure, and you can see your sand, silt, and clay are going to, sand, clay, and silt, I think is how it settles out. But anyway, you can measure how many inches of each of those you have in that cylinder, and you can calculate your percentages, and you can tell what kind of soil you've got in that sense. You can do like a home soil test. You don't have to pay $6 to send it off and have that done, but they're going to tell you a lot more. And it may be 12 now, I don't know, but still, it's never anything that's going to bankrupt you to have these soil tests done. So anyway, that gives you a basic idea, though. And then there's the spit test. I might show you that if we go to the creek sometime. You can get some soil in your hand, you spit into it, and you can do this. And as soil science students, they had us practice it enough, and against known varieties of mixes, you can get a pretty good idea of your mix just by doing that after you practice that a bit. Okay. So the farmers use that a bit. It's like, what kind of soil do we have here? Yeah, some silt in there. Not too much sand, is it? Yeah. If it's really sticky, it's too much clay. Yeah. Anyway. Okay. Um, so we have some terms for water in the soil. The first one is hygroscopic water. And this is the physically bound to soil particles that's unavailable to plants. So that's what I was talking about. I said clay can hold it too tight, is where the water can't get to the plants. So in clay, you're going to have some of this hygroscopic water, and kind of more in it than the other components, because they're not as charged. Okay, it's a charge that holds that in there. Gravitational water. This is water that drains out of the pore spaces after a rain. And so that's only going to be available for a little bit to the plant, and then it's gone. But again, that's kind of what's going to go on down through the soil, and do some of that chemical reaction against the minerals further down the soil, and it hopefully eventually wind up in the aquifer too, okay, to replenish what's lost out of there. The capillary water is what we're interested in for plant use. That's held against the force of gravity in soil pores, and that's available for the roots to take up as needed. How much capillary water is in a soil is going to be determined by that structure, their sand, silt, and clay percentages, and then how much organic matter, because like I said, that peat moss, that organic matter, um, helps hold water sponge-like. It doesn't hold it too tight, but it holds it. Okay. Um, Density of the soil and the type of vegetation around plays a factor. And then the location of underground water tables and how close those are to the surface. Some water tables are so deep down that you don't have, there's no root that is ever going to get there, um, even trees. Okay. Other water tables, your trees are definitely going to access that with their longer taproots. Um, some of our native grasses here have root systems that go down 6 to 8 feet or longer. I think there's some that exceed that even. And some of our water tables here are about 10 feet down. Okay. So those, some water tables are even a little closer to surface than that. I know at Stillwater, there was a water table at Perkins Road and where you turn, anyway, that one would, every time it rained, it, it would come out on the ground basically and say, well, that's just rainwater puddling there. But it wasn't. I mean, yeah, we had excess there, but it would stay there for a week, okay, after the rain. And it wasn't because it didn't drain or anything like that. It was just the water table was raised by the rain that much, and it would sit there. Because when I first moved there, I thought, wow, that's just a wet area. It's a puddle. It collects water, collects water. But then I learned as part of my class that is one of those spots where the water table just comes out onto the surface of the ground. In drier times, it'd go away. Here comes rain, and it'd be back, and it would stay there, till it got dry. And so, uh, water tables can vary from anywhere to very deep to right underneath the surface. Okay. And so that's what your plants are going to depend upon, is this capillary water. And I'm out of time, so I didn't quite finish. That's okay. Pick it up on Monday. Do we have questions on any